Right. Hello. So this is the fourth lecture and the last lecture of this course, the simple CTP course on anti-pseudo equations and integrable systems. So let's continue from yesterday. So yesterday we started on chapter 2 about, so we have defined what anti-pseudo-Young-Mills equation is, and in this topic I'd like to show some examples of integrable systems which are reduction of anti-pseudo-Young-Mills equation, and we have started with the twistor equation here, which is a second order PDE of two variables z and z tilde. So this is, I'd like to show that this is a reduction of anti-pseudo-Young-Mills equation on R22. So it so the manifold is the set R4 with a flat metric, and in this setting I'm using double null coordinates. So the flat metric is of this form, and the volume form on M is this one. Okay. And yesterday, okay, I think we have wrote down the anti-pseudo-Young-Mills equation in this case, which in the double null coordinates. So there are these three equations here, where this F, Z, W, so these are components of the curvature in these coordinates. And if we write the components of the curvature in terms of components of the connection 1 form, then these three equations become these three. Okay. So now my aim here is to show that this the twistor equation is a reduction of this system of three equations, right? And as we have still a lot to do today in 2 hours, so I have written quite a lot of things already. So let me try to go through this. First, I have to say, what do I mean by saying that this equation is a reduction of this system, right? So by this, I mean that there is a class of solutions. There is a class of solutions of this system that is determined by this equation. If we can show that there is such a class, then we say that there is a spatial condition that this system reduces to this equation, or this equation is a reduction of the system. All right, and so the anti-pseudo-Young-Mills that we're going to reduce to this one is the one with gauge group SR3R. Yeah, on the R22, like I showed before. And let me remind you that when we say the gauge group SL3R, so it means that we restrict the transition functions to take values in SL3R. And the bundle is a real vector bundle of rank 3, so each fiber is isomorphic to R3. And this gauge group, with this gauge group, we say that we will consider connections that are compatible, that are compatible in the sense that the components of the connection and the curvatures takes value in the Lie algebra of SF3C. And these, so this is the set of 3 by 3 real matrices with which are traceless. Yeah, okay. Right, and let me just go back. Now how to see that there is a class of solutions of the system that determined by this. an easy way is to see void answer. And there is an answer that does the job. And this is due to Maciek Dunowski in his 2002 paper. And so he wrote down this answer. And it is possible to show by direct calculation that the answer of this form, so the components of the connection one form of this form, it is with u is a variable, is a function of two variables, then this is a solution of the anti-pseudo-Yang-Mills equation even only if you satisfy the Tiseka equation. So you can just put this answer into the system here, and the whole system will reduce to this. So by this answer, so this answer has using this answer, so we can show that the Tiseka equation is a reduction of anti-pseudo-Yang-Mills equation. Okay. Now, but the answer itself is not does not give a clear or precise description to specify the reduction. Right. So let me say a bit of drawing from this example what we have to say to specify a reduction. That's choices. Okay, so right. So suppose I assume that I will consider anti-pseudo-Yang-Mills equation on R4 with a flat metric. Then well, to specify reduction first, maybe we should say about the signature of the flat metric, whether it is Euclidean or neutral. Then in the example above, I'm sorry. Yeah, in the example above, we chose neutral signature, so it's on R22. Okay. Okay. And then we should specify the gauge group, which in the above example is SR3R. Okay. And then the important condition that we should specify is about symmetry. What do I mean by this? So because we want, by doing the reduction, it means that we don't consider the general solution of anti-pseudo-Yang-Mills equation, but we have to give some condition that that restrict to a particular class of solutions, right? And one condition or one restriction that we can say that we say that the connection is invariant under some group of transformations on the manifold. For example, if we say that the connection D is invariant, for example, under translations along the W coordinates in our setting. And so translations are these transformations that we just translate along the W coordinate like this, where C is any real number. So this actually form a one-dimensional group. And we say that it's generated by this coordinate vector field. Okay, and it can be shown that if suppose D is invariant in this translation, there is a gauge or a choice of frame field, and we call this invariant gauge, such that the components of the connection one form is independent of W. Okay, this then, for example, for the Tiseka equation above, if we go up there, the answer, this answer that reduces anti-pseudo-Yang-Mills equation to Tiseka equation, we see that all the components are independent of W and W tilde, right? Because yeah, so it only depends on U of a function of Z and Z tilde. Then, so in this instance, so we have assumed that the connection is invariant under two-dimensional group of translations generated by these vector fields. Okay, and let me note here that the one might wonder what are the transformations that we are allowed to use. Here are their translations. So this is it relies on the fact that the anti-pseudo-Yang-Mills equation, the whole equation is invariant under the group of conformal transformations on M. And this means under conformal transformations, the equation stays the same. Hence, the transformation would map a solution to another solution. Then it's consistent to say that, okay, we will consider only a solution that does not change under this transformation. So when we assume the symmetry, we have to assume that the solution is invariant under subgroup of the conformal transformation on M, and translations are one of the conformal transformations. So it's okay to assume translational symmetry, right? And so let me refer you to the book by Mason and Woodhouse for full exposition of this, or the other kind of symmetries. And in their book, they have details of the reductions of various groups of symmetry. Okay. Now, another thing that we can specify is, apart from, I'm sorry, let me just go up. So apart from choosing a signature, the gauge group, and the most important thing is symmetry. And after we do this, then we can say more, like we can put some additional condition. So because for example, if I go up to this example, if I just assume symmetry, so I would have that the components are independent of W and W tilde, but then it doesn't have to be in this form. Then to put it in this form, then we need to put more conditions on it, right? And in fact, for this example, it is possible to give gauge invariant conditions that characterize this answer. Okay. That means that we just say that if the connection satisfy these conditions, then they can be put into this answer, right? And yeah, for example, and that condition is in the paper of Dunosky and myself in 2009. Okay. Right. Okay, so this is our first example. Let me go to the next example now. Okay. In this example, we have to go on to complex vector bundles. So all I have done before, I have only talked about real vector bundles and these pseudo equations on them, but you can formulate and these pseudo equations on complex vector bundles as well. And so let me just go through the definition of complex vector bundles. And I'm still considering the base manifold to be real manifold. The M is still smooth manifold. And in fact, what is given here is the same as what I wrote before for the definition of real vector bundle. So they're for complex vector bundle, so they are the same. Okay, I'll show you what changes in put in red. That for smooth complex vector bundle over a real manifold, yes, it is the same structure like for the real vector bundle, just that the fiber is now not a real vector space, but has to be a complex vector space. Then the local trivialization, okay, it's a diffeomorphism, but two, not not the product U cross Rn, but then Cn, because now each fiber is isomorphic to Cn, if it's complex vector bundle of Rankine. Okay. And just this, then if we restrict the local trivialization to each fiber, then it is now an isomorphism between complex vector spaces. So it has to be C linear. That's all. In fact, I think this should be C. Let me just change this. Yeah. All right. And given complex vector bundle, then we can formulate the pseudo-Yang-Mills equation in the same way as what we did on real vector bundle. There are details, but let me just summarize for our time that we have here, that in the, you just have to be what changes is that, say, for example, the section of the complex vector bundle now, when we look at local representation with respect to a frame field, like as a column vectors, now the components are functions, but not a real value, that are now complex valued functions. And the transition function would take value in a subgroup now of a complex general linear group. And then when we talk about vector fields, tensor fields, and differential forms on the manifold, now we use the complexified one. So the component functions of, say, the differential forms are now smooth functions, but complex valued functions. Right, so let me look at the second example of a reduction of anti-pseudo-Yang-Mills equation. It is Ward integrable chiral model, and this is due to Richard Ward in his 1988 paper. And it is this equation here. The dependent variable is J, which is a matrix valued function. So it's a function of X, Y, and T, and it takes value in SUN, the spatial unitary group. So that's why we need a complex vector bundle now. Okay, and so this equation is interesting. So it is integrable because Ward derived it as a reduction of anti-pseudo-Yang-Mills equation. So it inherits integrability by twistor theory, and it's interesting that it admits soliton solutions, and it also has a conserved energy functional. So you can assign a conserved energy to soliton solutions. So that's why it's interesting. Okay, so let me say, what is the anti-pseudo-Yang-Mills equation? What are the conditions on anti-pseudo-Yang-Mills equations that we can reduce it to Ward-Chiral model? So we look at anti-pseudo-Yang-Mills equation again. It's still on R22 with a neutral signature metric. But now in this example, it's more convenient to use Cartesian coordinates like x0, x1, x2, x3. Okay, and the gauge group is SUN. And the symmetry, in fact, as you can see from the equation depends on three independent variables now, where the anti-pseudo-Yang-Mills equation on 4 variables. So the symmetry is actually one-dimensional group of translation. So just one group of translations along the x3 coordinate. Yes. And then it can be shown that if the connection D, if we assume that the connection D is invariant under this group of translation, there exist invariant gauges that in those gauges, the components of the connections are independent of x3. So only depend on x naught 1 and 2, right? And to get the reduction that depend on 3 variables here, we say that we will stay in between invariant gauges, right? And if we stay in these gauges, then the transition, we require that the transition functions will be independent of x3 as well, okay? So what this does is that if we look at, in general, the component would transform under gauge transformation or under change of frame fields by this, like this. But now since G now is independent of x3, for the component A3, this term just go. So it transforms now just by conjugation, which is different from other component from A1, A2, A0, right? So it's kind of separate A3, like in a different kind of field. So this is called a Higgs field. And then, so with this assumption of symmetry, we now consider the components A0, 1, and 2, and then A3 would be, I would use a symbol phi because it now no longer is on the same footing as these because they don't change in the same way and they get transformations. Okay, and we look at them as functions on R21. So it depends on 3 variables. And this, I use R21 because we have an induced metric from this 4-dimensional flat metric above. So we have this induced metric. Yeah. Okay. Then with this, sorry, let me just. Okay. And then with this, we can just look at the anti-pseudo-Yang-Mills equation, which is this one in the Cartesian coordinate. Then, because now all the functions are independent of x3, these 3 equations will reduce to these 3, where a phi is a3, and then the covariant derivative on the Higgs field is given like this. Yeah, so this directly reduce it to this, just by zoom in independence of x3 coordinates. Okay. Right, so now we have a reduction, which is this system. So this system is a reduction from anti-pseudo-Yang-Mills equation by symmetry, translational symmetry along x3 coordinates, and it is called Yang-Mills Higgs system. Okay, so what is the Ward chiral model? Ward chiral model is actually the same as the Yang-Mills Higgs system. Yes, it's in fact I didn't write down the Ward chiral model, but let me go up again. Yes, so this equation, it is the same as the Yang-Mills Higgs system here, which we have seen that it's reduced from anti-pseudo-Yang-Mills equation. So how they are the same? They are the same under a gauge choice. And suppose now I call x0 as t, and then x2, x1, and y for x2. And then I claim that there exists a gauge such that this AT, which is A0, above here, it's like this, that the component of the connection 1 form is like this. Let me say it again. So there is a gauge such that there exists a matrix value function J that you can write the components into this form. Okay, So suppose we believe that there exists such a gate, then we just put this in here. Yeah, just to put this in there. The three equations will come down to just one. So we have the integrable chiral model. Right, so this is my second example of the reduction. Now, you might wonder that how do we know that there exists such a gate? And I would like to explain this too, but then I will do this using a lax pair for the anti-pseudo-Young-Mills equation. So I will go on to the next topic and talk about the lax pair. Okay. Right. Okay, so now I'm writing it here. So what are lax pairs first, right? First, maybe I just said lax. What is a lax pair? So a lax pair is an overdetermined system of equations such that, so if I say lax pair for anti-pseudo-Young-Mills equation, so it's an overdetermined system of equations such that the anti-pseudo-Young-Mills equation is the compatibility condition for the overdetermined system. And then many integrable systems have lax pairs, like say you can say about lax pairs for Sine-Gordon equation. So this is an overdetermined system of equation that the Sine-Gordon equation arises as the compatibility condition. Okay, so let me say a bit about compatibility condition for an overdetermined system. Maybe I start with the simplest one. Now, for example, if consider, and this is partial derivative with respect to f is a function of x and y in here. So suppose you have a system of PDE like this. G is some function. So in this system, the unknown is f, and g and h are given functions. Now, this system is overdetermined. It is overdetermined because you have one unknown, which is f, and then two equations. So it is more equations than we need. It's overdetermined. And in general, it might not have a solution. Okay. In general, I mean, if g and h are any arbitrary functions, then for some g and h, we might have a function that satisfies the system. Okay, so what would be condition on that we can put on g and f? Okay, one clear condition is a necessary condition. Necessary condition. Suppose a solution exists, then suppose I assume smoothness as well. Suppose f exists, and if f is smooth, then I know that the partial derivatives commute. It can interchange order. So if a solution F exists, and I assume smoothness, then we would have that if you differentiate, say, x and then y, it would have to be the same as y and then x. And because this has to be true, then it follows that G and H must be such that I try not to use the subscript for the partial derivative. Gy has to be the same as you differentiate H with respect to H, right? Okay, so this is a condition on G and H, a necessary condition. Now it turns out that this condition is sufficient as well for the existence of a solution. So it can be shown that this necessary condition is also sufficient. And this is Frobenius theorem. Okay. And things are similar if I change it to a system of vectors and PDE for vectors and matrices, what we would have for our connection, the antipseudo-Young-Mills equation. Right? So if you consider this system, so V is a column vector, n vector. So you have n components. And A and B are n by n matrices. But there are vectors and matrices of functions, right? So whose entries of functions. Functions of x and y. This is overdetermined again. So it's so we have n unknown. By n I mean like the components of v. If you say like v is v1 to vn, so n unknown. But then we have 2n equation. That's overdetermined. Now, by Frobenius theorem, the necessary and sufficient condition for this system to have a solution, the necessary and sufficient condition for the existence of a unique solution for each initial data. let's say for each initial condition, just is similar to above, like similar to the system above here, that this necessary and sufficient condition we can obtain by cross differentiating. Like we just look at necessary condition from cross differentiating, and then this will be sufficient as well. So, and let me just see. Right, if you we would, by cross differentiating, so we want this to be the same as this one, then if we compare, so this means that this has to be the same as this. Then if you compute that, what you have is this one. It's the condition on the matrix A and B like this. Okay, so this is the compatibility. We said it's the compatibility condition. And it is the condition that if it is satisfied, if A and B satisfy this condition, then we would have a unique solution for each initial condition. Okay, and we will use this for to describe the lax pair of the anti-pseudo-Young Mills equation, but just let me rewrite it in a form that is easier to use. So rewriting. I will not do much. I would just put this term to the left. So we have this, and then plus. And instead of writing minus A, let me just put it a new name, that PV equal to 0. Yeah, so it's the same as above, but just rewriting it in this form. I do this because I want to, we can look at this then as differential operator acting on V. Like, let me say D and subscript X, V, where dx is this differential operator. Okay, so it become this, and this one is dy v. Okay, and if I write it in this form, you can verify that the compatibility condition is actually it's actually that the differential operator commute equal to 0. This can be verified that this is correspond to this. Okay. Where the commutator, let me just. So what I mean by the commutator, I mean, just move it. Maybe, I'm sorry, let me just rewrite it. So this is the compatibility condition. So by the commutator, I mean if this act on V, it means that you act on V by Y first and dx, and then minus. Right, so let's look at So with this, let's try to I will try to give the lax pair for Andy-Young-Mills equation. So let me summarize again that the lax pair for Andy-Young-Mills equation is an overdetermined system of PDE whose compatibility condition condition is the Andy-Young-Mills equation. And let I formulate this on 2 and using double null coordinates. So we rewrite this. This is the flat metric in double null coordinates in volume form. Okay, and in these coordinates, the Andy-Young-Mills equation is these 3 equations here. Okay, so I want to write down an overdetermined system whose compatibility condition is the system of 3 equations here. And to see what they are, we can notice that suppose I letting the symbol D and subscript A to mean this. And I'm not sure. So this is the partial derivative with respect to XA for some coordinate. And this is the component of the connection 1 form in with this XA. So if we using the symbol, we have that the component of the curvature, which is this. This is we worked it out for from the last time. This one, but then it can be verified that this is the same as the commutator of this D here. Okay. This means if we go up above, here we have that this the 2 operator commutes like this is a compatibility condition of this system. Okay. And below, it can be verified this is just the commutator here. Hence, say the first equation, if wz equals 0, this is the same as, then it is a compatibility condition for the overdetermined system dwv equals 0 and dzv equals 0. Okay. So you could say that, maybe I just write it down. Letting this, we have that, say, so e.g. the first equation of the anti-pseudo-Young-Mills equation. This is the compatibility condition for this overdetermined system. Or we could say that this is a lax pair for just this equation alone. But now the anti-pseudo-Young-Mills equation is the three equations together, not just one. But then we can obtain the three by using some parameter. So let me just write down the lax pair for anti-pseudo-Young-Mills. So the system this equation. So D is that? Let me just write and then I will say about it. I'm sorry, maybe I changed the order. Okay, the system is overdetermined, but now I put lambda as a parameter. We add some parameter lambda into the system. Then this system is compatible for each value of the parameters for each lambda. So if and only if the commutator here, just keep the order. Vanish. Yeah, the commutative vanishes for each lambda. Okay. And if we now, I'm not sure we can. We can't see. Let me copy it down just to compare. Okay. If so now this commutator, when we compute this commutator, we would have the parameter lambda, right? And it will be a quadratic in lambda. So you will have term with lambda square and term with lambda and term with no lambda, like constant in lambda. And then each of the term has to vanish because we want it to be 0 for every lambda. And each of the term will be this. I mean, for example, if no lambda, you have that this equals 0, which will be this equation. Okay. Right. So this condition is the same as the anti-pseudo-Young-Mills equation. So just write it down. Let me just drop this. Oh, maybe I do this. So this is the same as the anti-pseudo-Young-Mills equation. And did you just say this is the lax pair that I want to talk about? So this is the lax pair for the anti-pseudo-Young-Mills equation because its compatibility condition is exactly the anti-pseudo-Young-Mills. Okay. just say so the system. So the system, I label the system L here. So the system is called the lax pair for the Anti-Pseudo-Young-Mills equation. Okay. Right, so now we have a lax pair. And so what is the lax pair good for? So now we just say, oh, it's okay so the Anti-Pseudo-Young-Mills equation is a compatibility condition for this system. But what is good for is that the geometric interpretation of this lax pair underlies the integrability of the Anti-Pseudo-Young-Mills by twistor theory. That's one thing. Another thing is that, in fact, the lax pair also provides a direct method to generate solutions too. And in fact, I want to really do this example of how you can generate solutions of using the lax pair. But to the example of the Ward chiral model. Okay. But let me just write a general idea for how to use the lax pair to generate solution. For in terms of Anti-Pseudo-Young-Mills lax pair first, and then go to the reduction to the Ward model. So a solution generating method. From the lax pair. This is based on a fact that, so suppose D is a solution of Anti-Pseudo-Young-Mills equation. This means the lax pair out above is compatible. So now by Frobenius theorem, by compatible, let me just go up. By compatible, so it admits a unique solution for each initial condition. But then we are looking at let me just careful for each initial conditions. But V is in fact it is a section of our vector bundle, but then in a local trivialization is represented by a column vector, yeah, or function here. So each initial value would be an n vector. Yeah, would be an n vector. So so there are n linearly independent initial value, and it can be shown that the solutions that we have will stay linearly independent. So actually, if the lax pair is compatible, there exists this lax pair admits n linearly independent column vector solution vector solution the V1 to Vn. Yeah. by linearly independence, I mean, these are vectors that V1 is a vector, and you have each component, the V1, 1, V1, 2. So it's a V1 is the name, and you have component up to V1, the n components, right? And each component of functions by linearly independent. I mean, when we evaluate it at a point, the vectors, they are linearly independent, right? And okay, so we have n linearly independent column vectors. This means we can form n-buoyant matrix solutions of the Lax pair. So the Lax pair here, let me just put. I write the Lax pair using, like, considering as a column vector solution. But since we have like n linearly independent of them, we can form a matrix solution here by putting the n vector solution as a row like this. So we can form n by n matrix solution. By putting our column solutions as columns of this. And because the vector solutions are linearly independent, this matrix is invertible. Okay. Then the anti-pseudo-Yang-Mills equation guarantees the existence of this matrix solution. And if we look at the Lax pair again, and I'm writing it now with the matrix solutions. And this matrix solution if we let lambda vary, so it will depend on lambda too. Now from here, I can extract. Remember that the dw is the differential with respect to w and aw, etc. Right. So if I write this here, we have this equation. We have this equation, which is right. I'm sorry, I think I must have writing something wrong. Yeah. Okay. And this is what we want for a solution of anti-pseudo-Yang-Mills equation, which are components of the connection. But so it just means that if, suppose there is a solution of anti-pseudo-Yang-Mills equation, the Lax pair will have this matrix solution. Then by rewriting this, we have this. That means that the information on the solutions of anti-pseudo-Yang-Mills equations can be extracted from this matrix solution. It's just by this computing the left-hand side. and then you have the solution. Hence, if we know a solution, somehow we know the solution, we can work out what are the connections that satisfy anti-pseudo-Young-Mills equation. So this gives a way to construct solutions of anti-pseudo-Young-Mills. Right. Now, but then a first question is to say that how would we know this matrix solution psi in the first place, right? Because if we don't know A, and how would we work out the solution? And a way to do it is to assume a form of this matrix solution and work it out. And there is a way to get to here. And I want to show this in the example of the Ward-Cairo model. Okay, which is the next. But I think it's maybe let's have a 5 minutes break before we go to this. And after this example, maybe I will have very least time to go to chapter 3, but I will just say something briefly. Okay, so I think so let's have 5 minutes break. So I will start again, say 7 part 3. Okay, so let's continue. At first, in this section, I like to show you. Let me just go to the. When we look at the Ward-Cairo model as a reduction of anti-pseudo-Young-Mills equation, and we said it's actually the Young-Mills system, which is a reduction of anti-pseudo-Young-Mills along translation of one coordinate. Okay? And the Ward model is a Young-Mills system under gate choice. So we pick this gate choice. And at first in that section, I would like to explain how to see that this gate exists. But then looking at the time, we won't have time now. I'm sorry that I will have to skip this. And I'll just go straight to see how to construct solution from lax pair, right? And let me just, okay. Sorry, I'm not sure why. Let me try to okay. Okay. So in fact, from here, I would want to derive the want to derive the Ward-Cairo model from the reduced lax pair. But let me just skip that and just say that the lax pair for Ward-Cairo model is what I'm going to write here. Lax pair for Ward-Cairo model. Maybe I should copy the equation for Ward-Cairo model to reference. Let me just take the Ward-Cairo model. Yeah. Okay, so this is the Ward-Cairo model, and the lax pair for the lax pair of the Ward-Cairo model is this. let me change this. Maybe, I'm sorry, let me just use the same symbol just in case I might refer to B2 and B4. Don't worry about 2 and 4, it comes from up there. Okay. Where U is, we change the coordinates, so U is half T plus Y, and V is a half T minus Y. And then, so curl U is this. Okay. And B B2 is in terms of the matrix J. And then B4. Okay, then the system which is the Laxpath what model. So the system is compatible if J in B2 and B4 appearing here is a solution of the Ward-Chiron model. Okay, and then if that is the case, there exists a solution, a matrix, invertible matrix solution psi to this system. And then from here, we can write it out. So if we know a solution psi, so I change coordinate from txy to xu and v with this and parameter lambda. Okay, so if we know a solution psi, you can rewrite this Lax pair and we can get what B2 and B4 is by rewriting the Lax pair like this. You can verify this later. Let me call the system with the symbol plus, just to label the system. Okay, by inverting this, we have, by rewriting this, we have this. That means if we know psi, we can work out B2 and B4 from psi. So let me say B2 and B4 are determined from psi in this way. And if we compare that B2 is just this and B4 is this, then it follows that I mean, because B2 is in terms of J and B4 is in terms of J like this too, right? And so it means J is determined from psi via these equations. And it follows that J, which is a solution of the word chiral model that we want, is given by psi inverse. And putting lambda to be 0. Okay. And this is a solution. If a solution psi to the lax pair exists, then the J getting from here will be a solution of what model automatically, because the existence of psi in the first place is due to the compatibility condition, which is a Ward model. So if we know a solution, this will be so if we know a solution to the lax pair, this J will be a solution to the Ward model. Now, come back to the same question, that how would we know a solution psi in the first place? But the thing is, we don't know, but then we can try to figure it out by assume some particular form of psi. And this was done. Let me refer you to this paper. This method of using the lax pair to construct solution was used by Richard Ward to construct soliton solution to the Ward chiral model. And this is in the details in the paper by Richard Ward. It's called soliton solutions in an integrable chiral model in 2+1 dimension by Richard Ward in 1988. The method is actually this way of finding solution is actually based on a method called Riemann problem with zero. By Sakharov and co-workers. Okay. Now the details, so what I'm written here is from this paper and the details in appendix. So let me just try to go through briefly. So the way to do it is to, well, we don't know psi, but then we can assume a certain form of psi, right? So psi will be a function of x, u, v, and parameter lambda. Then a simple case is to assume that psi had a simple dependence on lambda. So in Ward paper, he assumed psi to be of this form. So this is identity matrix. And then plus another matrix. And this matrix is of the form mu is just a complex constant. In fact, it has to be non-real. So it can't be a real number. It's a complex constant that are not real number. Okay. And lambda is our parameter. So this answer assumes that psi has just simple pole in lambda at mu. And the matrix here, n by n matrix, this identity, and this you obtain from the tensor product. So it's like you multiply a column vector. N is a column vector to a row vector. And M and N are not depends on lambda. So Mn do not depend on lambda. So the only dependence on lambda is in this pole, the simple pole here. Okay, now in components, you write it in this way. N, A, N, P. This is in components of the matrix. Okay. And let me just look at solutions, look at example where J takes value, no, for the word model, let me just go up. For the word model, J in general is a function from R to 1 to SUN. But let me just look at the case where N equal to 2, just for simplicity. So we have 2 by 2 matrices. So consider the case where J is from R to 1 and then to SU2. Well, this is what should I say? Since the word model is a reduction anti-pseudo-Young-Mills equation, so J will take value in SU2. This corresponds to assuming that the gauge group of the anti-pseudo-Young-Mills equation is SU2, which means we use this gauge group. It means that the components of the connections, this AA before we reduce, takes value in the Lie algebra of SU2. Now, these components are just the, let me just go. These components come down to this B2 and B4. So, so this means if I restrict to this example, I will assume that B2 and B4 takes value in the Lie algebra of SU2. So this corresponds to B2 and B4 takes value in the Lie algebra of SU2. And that just means that B2 and B4 are 2 by 2 anti-Hermitian trace-free matrices. Hermitian. And with this condition, and to achieve this, then we need to put some, because B2 and B4 now have to put. B2 and B4 are determined by psi, right? And if we require it to be anti-Hermitian and traceless, this will put condition on psi. And the conditions are this. Let me just write it out. So this is achieved by putting these two conditions. So one, the determinant of psi when we put lambda to 0. Yeah, the determinant of this is 1. This will give traceless condition. And then the second condition for anti-Hermitian, we just need psi to satisfy this equation here. Let me just write it out before. This give anti-Hermitian. Where lambda bar is the complex conjugate, and this star is the complex conjugate transpose. And you can verify it from, you can check that this, what I claim is true by using the Lax pair here. Complex conjugate transpose. Okay. Then if we impose this, we say that we want, so to use this method to generate a solution J, what we do is, so we say that we want to find a matrix function psi, invertible matrix function psi that satisfy condition 1 and 2. This means if we have this, then when we worked out, when we worked out B2 and B4 from it, it will be anti-Hermitian and traceless, what we want. Another thing we want is that we want psi such that the left-hand side of the system, so this is independent of the parameter lambda, because B2 and B4 do not depend on lambda. Yeah, B2 and B4 are just in terms of J, which is independent of lambda. So we impose these three conditions. So one is the first two is the one to make B2 and B4 anti-Hermitian and traceless, just because we want J to have value in SU2. And then the important condition is that we impose this, that here, which seemingly depends on lambda, is actually independent of lambda. And this will put condition, it will put equation actually on psi that you can work, that we can solve, and then it will give you psi that is solution of the Lax pair. Let me just so we want to find psi, satisfy first and second condition here, and then, and such that the left-hand side of this is the Lax pair, that this plus is the equation here that we just look at. Yes, with this one. Independent of lambda. So if we can find psi, this will be a solution to the Lax pair for some B2 and B4 then, and B2 and B4 in terms of J. And since the Ward equation is what Carroll model is compatibility condition for the Lax pair, then if we can find soil like this, the J that we work out from this will be automatically solution of the word model. And let me just outline what happened, and then the detail of this, if you're interested in this construction, the details in the appendix of the paper by Ward. In fact, I'm sorry, I will not have time to go on now, because I should say something about twistor theory and geometric interpretation of the lax pair. So let me just say that if we do this, then the result that what you have is this. Quantify this, and if you impose all this, what you have will be it. This is the result. The soil will be in this form. So this, I'm writing it in components. Yes. So maybe let me just try to go to write quickly. Okay, let me write this way. This is better. Sorry. So I will be in this form, the identity, and then plus mu minus mu bar. Mu. And then, you know, the answer we looked at. This is for some column vector n and tensor product with m, right? But if we impose all the conditions, it turns out that n is in terms of m. So what we have will be this. M, and then so m is a row vector, and this is we complex conjugate and transpose to have a column vector. Yes. And this is norm. And m does not depend on lambda, but m is depends on x, u, and v. And when we impose this condition, then just when we say that the left-hand side should be independent of lambda, yeah, so that we have B2 and B4. This will give a PDE to determine psi, to determine the dependence of psi on x, u, and v. And it turns out that psi depends on x, u, and v through this combination. Will be x. So m is a function. Let me just write this. M is a function of one variable, which is this x, the combination x plus mu u. Mu is the complex constant, which is the pole, and plus 1 over mu v. Okay. And so any psi like this, this psi like this satisfy the lax pair. So, and we can work out J from it, then J, which is psi inverse, and you put lambda to 0. This will be a solution to the word model. Maybe let me just write you one solution that maybe you can check that it satisfies the word model. Mu is any non-real complex constant. So you can put mu to I, for example. What I write down is a solution given in word paper. Where f is arbitrary function of this combination. The combination here. So x plus, and now I'm rewriting u and v to x to y and t coordinates. So it will be mu t plus y. Okay. And this is arbitrary function, so you can put f to be just this one, just this combination. Okay. Now this is a soliton solutions, and so it's give this is one soliton. So it's if you and I mentioned that word model is interesting because it has conserved energy. So if you plot energy density of a solution, you will see the solitons. You will see like alarms that moving, right? And you can extend this this solution to solution which give you more than one soliton, like 2, 3 solitons, and in fact you can adjust this to make a solution which correspond to solitons scattering. So more than one soliton, and there are interaction between solitons. And I think I will give you reference. Apart from war 1988, which is you have this solution, and then there is in this paper there are more solutions which exhibit many lumps, many solitons, but there are no interaction. But for interaction, there is a class of solution called n uniton. Is in the paper by Ward again 1995. Okay, and right. I think I will have to end here and say and spend the last 25 minutes on chapter 3. But before that, let me just show you some plot of the say 2 unitons of this solution of this model. Maybe I stop share this for the moment. And I showed you. Okay. Can you? Is it not big enough? Yeah. This is the plot is the energy density of the solutions, and this is a 2 uniton solution in what 1995 paper. So it exhibits the 2 soliton coming together and scattering at right angle with this one, and there are more like this. So I refer you to the papers. Okay, right. So let me, for about 20 minutes that I have, let me try to say a bit about geometric interpretation of the Lax-Pan twistor correspondence. Let's see. Okay, now I typed something. So for this, I refer you to Mason and Woodhouse and also Ward and Wales. And what I said will be just only general idea. So let me just try to be quick. We have been looking at the situation where M is real, a smooth manifold. But then to talk about twistor correspondence in the most convenient way is to go to complex. Now N will be C4, and then the metric will be a flat holomorphic metric. And now we will look at vector bundle. It will be complex vector bundle, but now it's over the complex manifold, and we require it to be holomorphic vector bundle. And this just means that before that, although we look at complex vector bundles, but since the manifold still is smooth manifold, or the maps that we require to be smooth, but now the maps, like say pi, which is a map, projection map from E to M, is required to be holomorphic. And then the transition functions, which that's why I'm sorry, let me say again, the local trivialization that we look at, before they were diffeomorphism, but now we require them to be biholomorphic. But the expressions of the antipseudo-Young-Mills equation and the Lax pair are the same. So this is the Lax pair that we looked at before. So let me write down. Now, I would try to say about geometric interpretation of these two equations. So suppose maybe I write this down first. So this, if I write it out, it is this and then minus lambda and then plus a double. This is this equation, right? Then if I look at this vector field, now holomorphic vector field, let me just I say that the expression for antipseudo equation and Lax pair are the same, but with now the coordinates are all complex now. Complex variable. Okay. Oops, sorry. And if we write the Lax pair out, we see this, and suppose I call this L. So that suppose let L to be this vector field lambda. This one, okay, yes, let's L to be this. For the first equation, the Lax pair, and let's M to be this vector field. For the second equation, the Lax pair. Then the Lax pair is actually a contraction of the covariant derivative with the vector field L. Right? And this one, the second equation, would be a contraction with M. And I think we have defined before in the previous days that this for this, we use the symbol like this. And it is the covariant derivative along vector field L and M. So these are covariant derivative of a section S along L, vector field L and M. So it says that the lax pair is actually a condition that is a condition that a section is covariantly constant along both L and M, along both vector field. Now, let me try to see. Okay, I think I have time to say this briefly. Let's see what this implies. So at the moment we have we have an implication that if the lax pair is satisfied, then we have a section that is covariantly constant along the direction of two vector fields L and M, like this. Okay, and let's see more what this implies. Okay. First, let's so this is the lax pair now. I'm writing in this way. Okay, so two along both L and M. But let's see first if we just have just one instead of two, just one equation here. So if and then, well, I prepared this that I like to explain this in the real case first, but then I will say that things follow analogously for the complex case, because the real case would look easier. So let me come back to here, that suppose in the back to the real case, and let X be a vector field, and gamma is an integral curve of the vector field. And integral curve of a vector field is a curve in M that at each point, the tangent vector to the curve is the value of vector field at that point. Yes, so the symbol means the tangent vector, and the curve is parameterized by t. So this is a tangent vector at each point, at the point gamma t, and it is the same as the value of a vector field at that point. Yeah, so given a vector field, then there exists integral curve, a curve like this, at least locally. All right. Now, then, this is a curve on a manifold. Just draw this. Let me just draw it here. So we have vector bundle E, right, over a manifold M. And suppose we have vector field on M, and this is gamma is the integral curve of a vector field. Okay. And suppose, and what this equate, if there is a section on a vector bundle that satisfies this, that is covariantly constant with respect to X, the vector field X, then if we restrict the section S onto an integral curve of X, yeah, so we restrict S onto here. It can be shown that it's So the section, let me write the section. But the section S is over here. If we restrict it to gamma, then its values at a point, say S gamma T. If S is a solution of this equation, it can be shown that its value at any point along gamma is completely determined by just one single value on a point. Oops. Say S naught. In other words, it means if we know a vector or on a fiber, then we can construct a section that satisfies this equation, right? And I'm sorry, I'm looking at the term now. And this is the case. Let me just write this. This is the case because if we look at this equation restricted on gamma, then this equation is actually a system of linear ODE. It's ODE in T variable there because we restrict to the curve. It's a linear ODE on T. And as a linear ODE, there's a theorem that there exists a unique solution for each initial data. So if we given a vector say S naught in a fiber of the bundle over a point on the curve. Let me just write this. Oh, section. And say this is gamma T naught, and this is a fiber. This one is a fiber. And if we just pick a vector here and use it as a initial value, yes, then there will exist a unique solution of this equation. So this means if S is a solution, the value at any point is completely determined by the initial value. Okay. There exists a unique section S that is determined by S naught. Yeah. That is a section S that satisfy the above equation. So S. Okay. Now, no, I'm running out of time. So let me just skip this and just say briefly about this. So this is an equation. This is what happens when we have the covariant derivative equal to along a vector field equal to 0, just one vector field. But for the lax pair, we have two vector fields, right? So let me, sorry, I would just have to skip this. Okay. Let me just use it. Okay, but for lax pair, we have two. And then with these two vector fields. Now it can be shown that these two vector fields will span the tangent vector of two planes in, now back to the complex one in C4. And these two planes are called alpha planes. Now this condition means that F is covariantly constant on each alpha plane, which is a particular two planes in the manifold C4 on each alpha plane. Let me just write, alpha plane is totally null plane. Maybe I just point it out here, just to. So what is an alpha plane? It is a self-dual with an F, self-dual totally null plane. By totally null plane, it means that any tangent vector to the plane, sorry, satisfy this, that we use any, G act on any pair of tangent vector will be equal to 0, and G is our flat metric. Yeah, this is totally null. And then self-dual is that any totally null plane, if we construct a two form from a pair of linearly independent tangent vector fields, then this two form will either be self-dual or anti-self-dual. And if it's self-dual, we call that plane an alpha plane. So this is an alpha plane. So let me just say that the lax pair is an overdetermined system, and it is compatible if the connection is anti-self-dual or a solution for anti-self-dual Yang-Mills equations. Hence, if you have a solution to anti-self-dual Yang-Mills equation, this is compatible, then there exists covariantly constant section of the bundle on alpha planes. Yes, and it's like what I show you here, that if it in one dimension along a curve, then it is, the section is determined by a vector, by just value at a point. It is the same over here, that you have a two plane. In fact, it is a two plane in C4, but for drawing, I'm just drawing two plane in real. So we have an alpha plane, and the solution of the lax pair is covariantly constant. It means that it's determined by just a value at a single point. So it's determined by just one vector. Hence, what we have here, let me just go straight. I'm sorry, but just maybe I would just say it myself. I'm sorry, just the last thing. Okay, since covariantly constant section on alpha plane is determined by just one vector, but then because the vector space is n dimension. Okay, so if the connection is anti-self-dual, there is a way to attach an n-dimensional vector space to associate in an n-dimensional vector space to an alpha plane. Okay, and what is a twistor space? A twistor space is a space of alpha plane. So this means that if we look at a twistor space, if we look at a twistor space, which is a point in here, is an alpha plane. Now over an alpha plane, we attach an n-dimensional complex vector space to it. So this gives a way to form vector bundles, complex vector bundles, in fact, holomorphic vector bundles over the space of alpha plane, which is the twistor space. And so with this, we have now, the time is over. So let me just say that we have the correspondence, and this is Penrose word correspondence. So Penrose is the originate twistor theory, and then but the application to anti-pseudo-Young-Mills equation is due to Richard Ward in this paper here. So there's a one-to-one correspondence between solution of anti-pseudo-Young-Mills equation. Now this is just the symbol here, just the complex C4 that I was looking at with the flat holomorphic metric. Okay. One-to-one correspondence between this and holomorphic vector bundle over the twistor space, which is the space of alpha planes in CM. Then, and it has to satisfy certain condition, which I will not say it here because we didn't talk about it before. But so one-to-one correspondence between solution and on space-time, and then holomorphic vector bundle over the twistor space. Right. Okay. I think I will have to end here as the time is over. And for this, for the about twistor theory, I would refer you to the two reference. Yeah. Right. So I think let me look at it. Yes, so it's well over now. So I think I will end the video just here. So thank you.